Yeah, wonderful. Welcome, everyone. It looks like we have got our chat sorted out. Um, my name is Jeremiah Fioravanti. I'm the president of the Delaware County Institute of Science. My professional affiliation is biology professor at Harrisburg Area Community College, HAC. I'd like to welcome you all here this evening. My bandwidth has been a little spotty all day, so if it cuts out, I will pass the torch to Dr. Anthony Lombardo, retired science teacher from Rose Tree Media. And of course, we have to extend our thanks to Laura Gurton and Penn State for hosting this Zoom webinar. This is the first of two exclusively Zoom webinars that we will do for our winter lecture season. Again, this is no small feat for an all-volunteer organization that was founded in 1833. It has a building that was built in 1867 at the heart of downtown Media, Pennsylvania. We have invited Dr. Kranz to come visit us next time she is in Pennsylvania to see our wonderful institute, as well as all of you in our chat who are attending. I'm going to encourage you all to become members and become involved as volunteers, to donate your time, efforts, or finances to help the organization thrive and persist into the future. Again, thanks go to Dr. Gurton and Penn State. And I want to remind you that we will have another speaker on February 12th, a wonderful talk about mathematics and ranked voting. I'll give a few more details at the end. I'm going to give a brief bio for Dr. Kranz. This was composed by Dr. Lombardo off the internet, so hopefully everything is accurate. Dr. Susan Kranz is an American mathematician who works in algebraic topology, knot theory, and algebra. She has over 20 publications and 5 research grants. She earned her PhD in 2004 from the University of California, Riverside. Currently, she is a full professor at Loyola Marymount University and has held visiting and sabbatical positions at the University of Chicago, MIT, and the National Security Agency. Dr. Kranz has received numerous commendations and awards as a distinguished leader in mentoring and community pathway building. She's mentored at all levels, including giving pathways presentations for middle and high school students in Los Angeles and teaching at the Carleton College Summer Mathematics Program for Women and the Summer Program for Women's Mathematics at George Washington University. Dr. Kranz has received one in particular award that has stood out. She has a character included in a deck of playing cards that features notable women in mathematics, published by the Association of Women in Mathematics. So I encourage you to please check that out. Dr. Kranz, feel free to correct me if anything was inaccurate in that statement, but you are very distinguished. We're extraordinarily happy to have you. It's one of the powerful things about Zoom is that you can attend across distances very easily and invite folks of just a wonderful caliber to speak in our distinguished lecture series. So thank you.
Thanks so much for the invitation. Thanks for the invitation. It's a real pleasure to be here. Thank you all for coming. I know that we're competing against a football game that's either starting soon or now. So I appreciate you taking the time to spend it with me here. Bill, do you have a question? Your hand is raised, and so I just wanted to check in first before we started. Okay, well, again, it's a real pleasure to be here this evening with you. And without further ado, what I'd like to do today is share some new-ish mathematics with you. So before we begin, though, I want us to get some practice typing into the chat. So what I'm going to do is I'm going to give you something to look at. I want you to think about the answer to yourself. Don't type the answer in the chat yet. We're going to count down together 3, 2, 1, and then I want you to hit enter on your answer. So you can go ahead and you can put your answer into the chat window, but don't hit return or enter until we're all going to do it together. Okay, so our warm-up question, our first warm-up question is, which one of these doesn't belong? So again, don't hit enter on your answer yet. Go ahead, put the number into the chat. All right, go ahead. 3, 2, 1, enter. Let's see everyone's guesses. Okay, so lots of 4s, lots of 1s. I see someone couldn't decide 4 or 1. Uh, so yeah, I agree with Ron that there's no right answer here. We can make an argument for all of these. Maybe you selected number 1 because it's a different color from all of them. Maybe you selected 2 because it was the biggest one. But again, the point of doing this is just to warm ourselves up and get us thinking mathematically, and to really drive home the point that, like, I know that we're led to believe in mathematics that there's always one right answer, and that's typically not the case once you leave school mathematics. Let's do another one. So same thing as before. So let's all go ahead. You can type your answer into the chat, but don't hit enter or return yet. All right, 3, 2, 1, enter. Okay, so let's see, lots of different ones. Yeah, so we can make arguments for all of these. Unfortunately, I think I don't know that any of you have the ability to unmute and share the reason why you came up with your answer. Um, it looks like 1 is the only one that has 3 sides, for example. 2 has more sides than 3. There's lots of different arguments that we can make for all of these. But again, really, I just wanted us to get used to the fact that, right, there's no one right answer, despite what you've perhaps been led to believe in the past. All right, so since I'm not quite sure how many mathematics speakers you have, although it sounds like you have one coming up to talk about voting theory, what I wanted to do was start off a little bit about just talking about math in general. We have a really good idea of what it means to do research in biology, right? Maybe you're looking at cells under a microscope, maybe you're working with animals. We know roughly what it means to do research in chemistry. Maybe there are some test tubes involved. The physicists have all the great toys where they get to spin things around, put things in particle accelerators. But what does it mean to do research in math? And some other questions: what does it mean to discover new mathematics? And what do mathematicians do all day? What does it mean to be doing math? These are questions that I talk about with my students as well, because so often they'll come into a calculus class and they think all math is known. It's in the books. It's in the textbooks that they're going to use in their class. So I'll give you a moment to read this comic about mathematicians. All right, so lots of people think that math is about numbers, and there are some numbers that are involved in math, but I like to think about mathematics as being about patterns. So what do mathematicians do? They look for patterns, they try lots of examples, and then they make conjectures or guesses as to statements that would be true. So let's look at this example here. So suppose we were going to add up some odd numbers, and let's look at the first row, right? When we add the first row, we're going to get 4. And then when we go down to the next row, we'll get 9. And we can continue doing this. 16, 25, 36. And so the question is, right, what's the pattern here? What are we seeing is going on here? So if I want to add up to any odd number of my choice, what's going to go in those question marks there? So if anyone has a guess and wants to type it into the chat, go ahead. So what we're looking for is, what's the pattern with these numbers in the right column? What do you notice about those numbers in the right column? Good. Anyone besides Walt? Yeah, good. Great. Yep, these are square numbers. So what goes there is indeed n squared. And so this is a nice fact that mathematicians, identified and are able to actually prove. But maybe you agree with us, our friend Steve Colbert here, that maybe you don't like equations so much. And that was the thing that perhaps, turned you off about mathematics. in the past? Well, there's a really nice way to describe this fact that we just discovered geometrically. And we can do it using some dots. So if I just have one dot, that's not so interesting. Doesn't really look like a square yet. But now when I add to that one, the number 3, we see that now we have 4 dots, and that indeed makes a square. And then if I again add 5 to that, make a new part of my square, and so on. And so we have this picture argument that shows what we noticed with our table. Let's look at another example. So let's just stare at these numbers for a little bit. Notice that the numbers in the right column are even, and the numbers in the left column are sums of primes. And so we can try this again. So if you think to yourself the number 16, can you write 16 as the sum of 2 prime numbers? So think to yourself for a second, are you able to add 2 prime numbers to get 16? And if you want to type a way of doing that into the chat, feel free. You should feel free to participate in the chat as much as you feel comfortable doing. It's nice to be able to interact with you all. Good. And so it'll turn out that if you try this with other even numbers, it's going to work out. And so this is a statement that was developed back in the 18th century, that every even integer greater than 2 can be expressed as the sum of 2 prime numbers. What's sort of incredible is we have not been able to prove that this statement is true. So we can use a computer, we can test tons and tons of examples, and it all seems to check out. But we have not come up with a definitive, 100% verification that this statement is true. And so, this is one of those things that I love showing to my students as a way of illustrating that, nope, not all mathematics has been done and is known yet. There's still lots of mathematics out there for us to continue thinking about. The next thing that mathematicians like to do is they like to ask questions. So typically, the way that we do this is we start with something that we do know, for example, the Pythagorean theorem from our high school geometry classes. And hopefully, at some point, you've seen what the picture version of this, that if I take squares whose side lengths are the sides of my right triangle, what the Pythagorean theorem says is that the area of the yellow square is equal to the area of the green square plus the area of the blue square. Okay, this is something we learn in high school. And so what do I mean by ask questions? Well, I mean, okay, now what if instead of drawing squares there, what if we replace those by circles whose diameter is the length of the side of the triangle? Is it still true that the area of the yellow circle is equal to the sum of the area of the green circle and the area of the blue circle? What if we instead put equilateral triangles? Okay, is it still true? So what we like to do is take things that are known and tweak them just a little bit to get a new question and try and decide whether or not the answer to that question is also true. Okay, so now having said all of that, I have 2 stories that I want to talk about this evening, about 2 different patterns that we can see when using tilings, for example, of the floor. So I'm going to put this website in the chat, and I want everyone to click on it. And when you do, you'll see something that looks like this over on the left. So when you click on the word geometry and then click on polygons and shapes, you'll see a drop-down menu with lots of different shapes. So let me, in fact, let me show you what that will look like. I'll stop sharing my slides and instead share the website. Okay, so you'll get something that looks like this, and you can just drag and drop whatever shapes you want. And then you can rotate them. And you'll notice that all the side shapes are the same length, and so they can click into each other. So I want us to play around with this website for a little bit. In particular, what I want us to do is I want us to focus on these 6 shapes at the top. So these are all called regular polygons. The word regular means that all the side lengths and all the angles are the same as each other. And so my question for you, and again, I want you to take some time and play with these by yourself first. I don't want you to type anything into the chat yet. I want everyone to be able to have the moment of discovery for themselves first. Suppose you were going to tile your bathroom floor and you only had enough money in your budget to use one of these shapes. So which one of these 6, or which ones of these 6, could you use by themselves to tile your bathroom floor? So go ahead, take a moment and try that out by yourself for a moment before we type anything into the chat. Let me draw a line there. So let's do the same thing that we did before. Let's type any guesses that you have into the chat. If you don't remember the name of the shape, that's okay. You can say what color it is. And let's see what folks come up with. So go ahead if you have guesses for which of these will work by themselves. Any other guesses? Okay, so let's see, we've got a few guesses, and so let's check. So yes, if you take a square and you use that, many of us perhaps even have squares on our bathroom floors, but squares will work for a regular tiling of the floor, as will triangles. A few of you said that in the chat, and as will the hexagons. Now, it turns out that unfortunately, if we try the pentagons, the 5-sided figures, that's not going to work. We're going to have this little gap here that we're not going to be able to fit in another hexagon. Let me show you. I'm sorry, pentagons. The pentagons will not tile the floor for us. We just don't have enough space in between that little gap. And so what this leads to is a question: can we find convex pentagons that do actually tile the floor? So we're not going to limit ourselves to ones that are regular, meaning that all the sides and all the angles have the same length or the same measure in terms of the angle. What if we allow some flexibility there and we allowed our side lengths to change and also our angles to change? And this question inspired a quest that began about 100 years ago. So in 1918, there were 5 families of such pentagons that worked, and they were discovered by Karl Reinhardt. Now, even though they're colored differently, these are the same shape. Okay, so the coloring is just for aesthetic purposes. So these are 2 of them, and these are the other 3. So if you notice, again, all of these individual tiles, right, they all have 5 sides, and they have different lengths of the sides and different angles. Okay. Then 5 decades later, okay, Kirschner came up with 3 new families. So here they are. And at the time, Kirschner declared that the 3 families that he found were it. That the 5 that were discovered 50 years ago, together with these 3. So these total 8 were all of them. And so this caught the attention of Martin Garner. And now Martin Garner had a column about recreational math called Mathematical Games that appeared in Scientific American. And so he published this result, that the problem was solved. Here they are, the 8 families. Well, now his column inspired his reader not to take this result at face value. And it turned out that that was actually wrong, okay? There were more than those 8 families, and his readers wrote in and found some others. So James discovered what is now called the 10th family. And it turns out that this family of tilings appears in a project at Ohio State University. In their math building, it has 7 floors. On each floor, they have a different tiling pattern. So when you get out of the elevator and look at the floor, it is, completely different from any other floor of the building. And there's a little plaque there that tells you about the specific tiling. And so they chose this one for the 6th floor. And this brings us to the first mathematical hero of the talk, a female mathematician, Marjorie Rice. It turns out that she actually had no formal training in mathematics. She was just an amateur mathematician. She loved working with puzzles and things like that. She was a housewife, and she sent Martin Garner these 4 new families. So what Martin Garner did is he showed all of his correspondence with Marjorie to a mathematics professor, Doris. And Doris took all of that correspondence and shared it with the greater mathematical community at large by publishing it in a journal. So if we look at this pentagon that Marjorie found, its tiling pattern looks like this. And so my puzzle to you is, what do the tiling patterns for the rest of her discoveries look like? And we'll have some time in just a minute to go back to that website, and you can play with them there. So you'll notice over on the left side in the menu, if you hide the submenu polygons and shapes, there's a pentagonal family. So you can actually try doing all the tilings with these pentagons. Okay, so the story continues. In 1985, we found the 14th family. And then this story went cold for 30 years. And it wasn't until a team of faculty and undergraduate students working together discovered this 15th family. And this was big news. So it appeared in The Guardian. It also appeared in Forbes. And now you can find it gracing the sides of buildings as a decoration. 2 years later, a mathematician came out and said, you know what? Now we're done. We really are done. We found all the convex pentagons that will tile the plane. And it was the work of Michael Rao. And he published an exhaustive search that showed that this was all of them, and the story really is complete now. So what I want to do is just pause for a moment and give you some time to try dragging some of these into your little workspace and see if you can get the tiling patterns to work out. So again, pick one of them and then make lots and lots of copies of it and see if you can move them around and get them to work. So let's pause for just a second and give you some time to try that. And if there are any questions as you're looking at those, I'd be happy to answer some now. You'll see on the screen that I've labeled the pentagons that Marjorie Rice was responsible for, and then also the final 15th one that was discovered, again, recently-ish, I would say. Laura, do we know, is anyone able to share screen if there's anyone who is getting a tiling pattern to work and would want to share their screen with us? And John, that's exactly right. That actually the paper that Rao wrote has not been completely verified to my knowledge yet. So he performed an exhaustive search using a computer, but it has not been 100%. So perhaps that is true. That is true. Let's see. I know that a good friend of mine, Tom Edgar, is here. I don't know if he has any updates on that, but the last I had heard was that this was still under consideration. Tom, if you have anything that you want to chime in with. No problem. And yeah, I don't know if any of you are able to, I don't know if guests are allowed to share screen and show us the pentagons that tilings that you've come up with.
I would need to promote them, but
Oh,
if they
okay.
put in the chat that they have something, then I can temporarily promote them, so they should be able to share screen.
Oh, okay. Yeah, if anyone wants to share with us, if you've gotten one of these to actually tile some of your screen so that then we can see what the pattern looks like, feel free to chime in and we can share. All right, well, now let's switch gears a little bit and move to a different story. So again, this pentagonal tiling story dates back about 100 years, seems to have been solved, within the last decade, 2017. So now I want to turn to a story that dates back about 80 years ago and was actually solved just last year. So some of you might actually be familiar with this story. So let's start by remembering these tilings that we've been talking about. So the triangles, the squares, the hexagons, and these families of 15. These are all examples of what we call periodic tilings. And mathematicians have known about and been interested in periodic tilings for a long, long time. What the word periodic means is, imagine that I made an overhead transparency. I realize I'm dating myself by saying what that is, of one of these pictures. And I just picked it up and slid it over and put it back down on top of my bathroom floor. It should match up identically. Okay, so periodic means that I just have copies and copies and copies of the same thing over and over again. And again, mathematicians have known about these for a long time, and these are very well studied and understood. And then sometime in the 1960s, there was a philosopher, Hao Wang, who asked the question, is it possible for us to have a finite number of shapes? Okay, so maybe we've got a pentagon, maybe we've got some other shapes, but finitely many, so we can't have infinitely many of them, so that the only tiling patterns on our floor that are permitted by these shapes are not periodic. So they don't have this property that I could imagine picking up a copy, translating it over, putting it down, and have it match up. Okay. Now, he thought that this was impossible. And a few years after he posed the question, his PhD student actually showed that such a thing was possible, but it took him about 20,000 different shapes to make that happen. But he quickly brought the number down to about 100 different shapes. And so the question then in the minds of mathematicians was, well, what's the fewest number of shapes that we could use? And in the 1970s, Roger Penrose brought the number way down from 100. So here is a tiling pattern that uses 6 different tiles or shapes. And it's such that if I made a copy of that and picked it up and slid it over and put it back down, it would not match up. A few years later, Penrose got that down to just 2 different shapes. So the challenge then became, can we get this down to a single tile? So the catchphrase was, can we find an aperiodic monotile? So monotile means single tile. Aperiodic means not periodic, doesn't satisfy this property. So in November of 2022, David Smith found such a tile. And this was called the hat tile. So let me pause for just a second. If you know this story, can you let me know in the chat? Did you see the announcement about this? Is anyone aware of the rest of the punchline of what I'm gonna, don't steal my punchline from me, but just let me know if you were familiar with this story. Nope, great. I'm so excited to get to share it with you then. So David Smith is not a mathematician, again, just like Marjorie Rice, interest in puzzles and mathematics. He's retired. He had been thinking about this challenge, this question, since about 2016. And so we had been working, and notice that in this picture of him, right, he has cutouts that he was using on his kitchen table. And again, in November of 2022, I almost said last year, he came up with this hat tile. Now, some of you might argue that it actually should be called the t-shirt tile, but naming aside, he then brought his shape to the attention of some mathematicians and Joseph Myers, who is a computer programmer, to say, look, this seems to be working out, but right, that's not a verification, that's not a proof. Can you help me look through all of this? And so it was in March that they posted online a mathematical paper where they rigorously show that hat shape really, really does do the job. And the internet exploded. So you could get news about this anywhere. It was on CNN. For those of you who watch late night television, Jimmy Kimmel had a monologue about it. I have the video all queued up. So at the end, if anyone wants to see it, I'd be happy to show it to you. And you could find anything that you wanted on Etsy in the shape of this new tile. So you could find a quilt, you could find cookie cutters, you could find mugs with the pattern, anything that you wanted. Even at the end of last year, so in just like 3 weeks ago, the New York Times had an article where they posted pictures of all of the different things people had done last year using this new shape. So these are actually ravioli in the shape of the new tile. You'll notice that the article title calls these an Einstein. That's German for one and shape. So it was a single shape that tiled. But I encourage you to check this article out if you're able to access it. There's lots of really fun ways that people use the hat in their work. Now, there was this teeny issue with the hats that led some people to be like slightly less excited about it. If you look at the t-shirts or the hats that have the red stars on them, notice that as we're looking at them, the sleeve on the right is sort of the longer, thinner one. It looks like the one on the slide, the big version. Whereas if you compare that to the dark blue t-shirts, they have this sort of longer, thinner sleeve over on the left. So this is the mirror image of the t-shirt on the top. And so people who were, real sticklers were saying, actually, it's not just one tile. It's really two. It's the tile and its mirror image. Okay, so right, there was this question, or maybe folks were a little less enthusiastic than when the announcement first was made. But even better than the announcement of the hat tile was the fact that this team of 4 discovered that there wasn't just one shape that worked. There wasn't just the hat. There's an infinite family of shapes that work by just slowly deforming the hat into other shapes. And this is one of them. This is the turtle. The turtle also has this same property. And on that New York Times announcement article, there's a lovely video at the end where they show you how the shapes morph from one into another to get just this huge infinite collection of shapes that do the job. Okay, so then, right, then the new challenge in March became, okay, we have this one, it works, but we have to flip it. Can we find one that we don't have to flip? And it took the team just a couple more months to come up with a shape that actually really, really did the job and answered the question and, shut the door on this mathematical quest. And it's called the Spectre. And how did they get the Spectre? Well, they started with a shape that they had already known about from the turtle hat family, and they added these little wiggles into it, and then they smoothed it out a little bit, and so that led to the Spectre. And so you can find articles on the Times and other places where they have the tiling pattern and show you where these arose from the hat tile. Okay, and let me stop sharing this and bring you back to our little play area here. You'll notice down at the bottom, we have the Einstein hat tile. So you could try and do the tiling for this. Remember that if you want to try with the hat, you're going to have to flip it. So you're going to have to make some copies that you flip it over. And you might even be able to, change the color of the ones that you're flipping so that then you can keep track of the ones that are flipped. Okay, but so they do not have the Spectre tile here, but you can definitely spend some time playing with the Einstein hat tile and seeing if you can get that pattern to work out. All right, so those are the two stories of, fairly recent mathematical discoveries that were made. Again, I love sharing this sort of thing because, especially with my students, it really drives home the fact that mathematics is being discovered and created all the time by all sorts of different people, right? These two stories introduce two folks that just have a love of mathematics, but no formal training in mathematics. And they were able to make these huge discoveries in the field. So thank you so much for your time this evening, and I'm happy to answer questions either about this material or other mathematical questions that you might have.
Thank you for that wonderful lecture.
Yeah. Thank you. If anyone has any particular questions, you may enter. I know it's difficult probably to be concise with your questions, but if you do, feel free to place them into the chat. Dr. Kranz, the only caveat to having a Zoom lecture, you can't hear the amusement of your audience as not only the puns or not only the excitement of realizing that people just get together to make these tiles and try to outwit. And it's taken so many decades and decades of energy and time. I believe there's one question that some people may have, and that is, I'm sure it's not just a group of mathematicians at the local pub saying, okay, let's try something new here. There have been practical applications of such tilings, I'm sure. Do you have any knowledge of some of the more nouveau tilings that have ventured their way into engineers' hands and dealt with some other issues?
Yeah, so I'm the wrong person to ask about this. Some of you might know that there are, these two branches of mathematics. There's applied mathematics. I have many friends and colleagues who study things like mathematical biology or, model cancer or other things. And then there's those of us, and I'm in this other camp over here, that are more pure abstract mathematicians. No one is going to be calling me up or knocking down my door for my research to have any practical application to the real world. And so what I like to liken that to is, for me, mathematics is more like an art. In the same way that we like going to a museum and seeing paintings, going to a musical performance or an opera, going to a park with open grassy spaces. We enjoy these things because we enjoy them, and they bring us joy and enrichment to our lives. And so there's so much in mathematics that falls under that we are just, delighted and tickled to discover these things, especially questions that were asked, decades ago that we can now answer. And so, right, I don't know if you decide to tile, something with one of these shapes, right? Is anything going to make anything better by some measurable amount other than just your delight in walking into your kitchen, knowing that you have this new tiling pattern?
Well, it's also heartwarming to see that mathematics is not just for the mathematicians, and the contributions made by the individuals that you portrayed is extraordinary. They can't say that necessarily occurs with other disciplines, but it's probably more ubiquitous than we realize it to be. So it's wonderful to hear. Okay.
John, great question. So it turns out, amazingly enough, we're especially delighted by this fact that it's about the golden ratio number of times that you need to flip the tile. So it's like 1 out of every 7 tiles do you need to have flipped the hat. But you can get online, an incredible grid of many of them that you can just that have the flipped one colored, and you can give it to your contractor. But I have certainly had the thought of having some room in my house tiled with that tile, but needing to then explain it to someone. Yes.
Oh, that's extraordinary. Escher's lizard drawings. Of course.
Yeah, so I would have to look more carefully at the Escher's drawings to see which ones are periodic. But again, if you could imagine making a photocopy of it and then just picking up and laying it down over on top of itself, and if it matches up, then it's periodic. So I'd have to look at which Escher ones you were talking about.
Okay.
And I mean, if we have the time and the interest, I'd be happy to play the Jimmy Kimmel little clip announcing. Yeah, so let me see
That'd
if
be
I
wonderful.
can advanced share. Let me video.
I'm just going to go ahead and pause the recording because we won't be able to show that material.
Oh, okay. Oh, right, because it's not right. Yes. Great. Let me know when it's paused.